Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Acid-catalyzed dehydration of alcohols proceeds via carbocation intermediates, and the major product is determined by carbocation stability and Zaitsev's rule, most substituted stable alkene. Moving on to the next step. Protonation of the alcohol. Under H+ heat, the OH to cyclohexyletanol is protonated to give a good leaving group, water. Moving on to the next step. Loss of water to form a carbocation. Initially, a primary carbocation would form at the terminal carbon, CH2+ adjacent to the ring, which is very unstable. This undergoes a 1,2-hydride or 1,2-alkyl shift. And for the final step, ring expansion via 1,2-carbon alkyl shift. The primary carbocation at the exocyclic carbon triggers a 1,2 shift of the adjacent C to C bond of the cyclohexane ring. This ring expansion converts the primary carbocation into a more stable secondary carbocation now incorporated into a 7-membered ring, but more relevantly, the shift produces a tertiary carbocation at the ring junction, effectively giving a cyclohexyl carbocation with exocyclic character. Actually, more precisely, the substrate is cyclohexyl CH2CH2O. After protonation and loss of water, a primary carbocation forms at C1 of the ethyl chain, i.e., CH2 plus CH2 attached to cyclohexane. A 1,2-hydride shift from the ring carbon to this primary carbocation gives a secondary carbocation directly on the ring carbon bearing the ethyl group, CH, plus, on the ring with CH3 or a secondary carbocation on the carbon alpha-2 ring. The carbocation that forms after 1,2-hydride shift from the exocyclic CH2 gives a tertiary-like carbocation on the ring carbon, secondary in ring plus adjacent substituent. Specifically, the ring carbon bearing the CH2 group becomes the carbocation center, secondary carbocation at the ring, with the CH3 group now pendant. Elimination, E1. Loss of a proton from the adjacent carbon gives the most stable, most substituted, alkene. The resulting alkene is cyclohexylidenetane, i.e., a cyclohexane ring with an exocyclic double bond, is equal to CH3, which is 1-ethylidecyclohexane. This is a trisubstituted alkene, and is more stable than the terminal alkene, vinylcyclohexane, by Zaitsev's rule. Why other options fail? A. Vinylcyclohexane. This would result from simple dehydration without rearrangement, giving a less substituted, terminal, alkene, not the major product. C. 1-methylcyclohex-1-Na. This would require ring contraction or a different rearrangement pathway, not consistent with the straightforward 1,2-hydride shift mechanism here. D. 4-methylcyclohex-1-Na, same issue as C, does not follow from the expected carbocation rearrangement. The major product is 1-ethylidecyclohexane, cyclohexane ring with is equal to CH3 exocyclic double bond, option B, because the 1,2-hydride shift converts the primary carbocation to a secondary ring carbocation, and subsequent E1 elimination gives the more substituted exocyclic trisubstituted alkene. Therefore, the correct answer is B. Therefore, the correct answer is option B.